As we have seen this in the last video, that the total length of IP header including the data could be 65535, because the total length field was allowing our 16-bit, which means I can represent this as a maximum number. If there are all ones, then I can represent this as maximum number, which means 2 power 16 minus 1, which is just 65535. This is what we have seen in the last video. But there is some problem. I mean, if we are using some protocol at the data link layer that you or anyway have to use, then there are some limitations that data link layer protocol provides, which means some of the protocol do not allow like more than some value. Suppose I'm using Ethernet, okay, Ethernet as a protocol at data link layer, then in that case it allows only 1500 bytes, 1500 bytes as a data. So when I'm saying that as a data, which means it includes header, IP header and IP data. So this as it is payload. So payload is basically a common term that we can use at any layer. So I can say the whole thing is payload also, because the payload is a common term that we can use at any layer. Now what I'm saying here is that Ethernet is having this much as a limitation, that it can allow only 1500 bytes as a total data. So obviously like apart from the header, which means if you exclude this IP header, then it can allow, suppose the IP header is only 20 bytes, it can range from 20 bytes to 60 bytes, but I'm assuming it is just 20 bytes. Then if we are using Ethernet at the data link layer, then it will allow only 1480 bytes as the data in the IP, right? So like this, the total length of the IP data including the header, or without including the header if you want me, then you can just subtract 20 from this number. So including the header, the total length could be this according to IP. But if you are using the Ethernet as a protocol, then this is not as a total length we can use. We can use only 1500 bytes as a total length, which means if you do not include this header, then you will be using only 1480 data bytes in the IP, right? So this is the limitation that is provided by the data link layer protocols. So depending on the data link layer protocols, we have the limitations. Now let me go to the next page. So suppose that you are using Ethernet. So Ethernet will say that I am only allowing 1500 bytes. So here 1500 bytes are allowed, which means from the IP perspective, this will be the IP header and this will be the IP data, which means data could be 480 up to 480 only, because if you take this as a minimum, IP header is a minimum value which is 20, then data could be up to 480. And let's suppose it is also using the, like this data is also using the TCP header. So this will be the TCP header in this 1480, and TCP minimum size is also 20 bytes. So this will be 1460, right? So this is the data that I can allow at the TCP, and this is called segment. So the maximum segment size, this is called maximum segment size, MSS. So maximum segment size, if we are using Ethernet, then it could be only 1460, right? So how we determine this maximum segment size? Based on the protocol that we are using at the data link layer, and this is called MTU. This is called MTU, maximum transmission unit. So what is maximum transmission unit? It is amount of data that data link layer protocol allows, obviously without header. So this is without, see, MTU, MSS, these are without headers. So MTU is at data link layer and MSS is at transport layer, and you can say that MSS is determined using MTU. Okay, so I hope you got it, because like at the data link layer you have MTU, which means that it is the amount of data that data link layer is allowing, and at the transport layer you have MSS. So both are without the header, and at the data link layer this is without the data link layer header, at the transport layer this is without the transport layer header. So both are without the header, and this is the amount of data that these protocols are allowing. Now there could be some other protocol at the data link layer which is allowing some other data, some other length of data. But from IP perspective, you can have 65535. Up to 65535 as a total length, which means if you just subtract 20, then you will say 65515 as a length of IP data that you can have at maximum, because minimum 20 bytes you need to have as a IP header. But if you are using Ethernet as a protocol, then this is not 65515, this will be 1500 only. So anyway, like this number is not important. This concept is important, which means that if you are using some protocol, then this every protocol has some MTU, which means maximum transmission unit. And if you are using Ethernet, then it just allows 1500 bytes as a data. Which means if I ask you that what is the amount of data you are allowed to use at the IP layer, then you will say 1480, the maximum amount of data that you can use at the IP layer, right? So this is the concept related to MTU and MSS. Now what happens that suppose your data from the IP is containing more than 1400 bytes. Suppose this is 5000 bytes and you are talking about the source only, and then this is the IP data, right? I mean IP header, and then this whole thing has to be carried in the Ethernet frame. Suppose this whole thing has to be carried in the Ethernet frame, then there will be Ethernet header, then this total cannot exceed 1500 bytes. But this total is, suppose this is 20 bytes only, then this total is 5020 bytes, but it cannot exceed 1500 bytes according to the Ethernet. Then what we need to do, we need to part this data. I mean, we cannot part this header will be as it is for every of the fragment. So what will we do, what will we be doing, we will be parting this data, and these are called fragments. So this IP header will get glued to every of the fragment as it is, which is of 20 bytes. So we will be parting this data into 480, so that the total should be 1500 only. 1500. So this will be 480, this will be 1500, and this will be 480, this will be 1500. And now if you multiply this 480 into 3, then there will be something that will be remaining. So this will be the remaining data, and then this will be 20 bytes, right? So this will be like something which is I think less than 1500, but it doesn't matter. So basically maximum size could be 1500. So we will be dividing this 5000 bytes into 4 packets or 4 fragments, and this process is called fragmentation. So what we are doing, if we are getting data that is larger than what is allowed at the data link layer, then we are dividing this packet into number of packets such that we can accommodate this data into one Ethernet frame, right? And this process is called fragmentation. Now this is at the source side. So fragmentation can happen at the source or maybe at in between the router. So which means suppose that there is some network and this is the router, and this is the packet that is coming to the router, and this packet is suppose having some data which is like each data is containing the Ethernet frame, and which means the total data is just less than 1500 bytes. But this network is not even allowing the 1500 bytes. So maybe the MTU at this network is suppose like 1000 bytes. Then what we will be again dividing this data into number of packets or number of fragments. So we will be dividing this into 2 fragments so that we can allow this packet to pass through this network, because this network doesn't allow more than 1000 bytes at the data link layer, which means the MTU is 1000 bytes only, right? So the fragmentation can happen at the source side, or maybe it can happen at the router side. And in the this is the case of IPv4. In case of IPv6, the fragmentation only happens at the source side. So this is the scenario about the fragmentation. Now generally what happens that we avoid the fragmentation at the source side, which means like if we already know what kind of data link layer protocol that we are going to use at the source, then what we do, we do not supply more than 1500 bytes if we are using the Ethernet. So at the network layer itself, like we do not supply more than 1500 bytes, which means this is the IP header and this is the IP data, which should be at max 480, which means at the transport layer I will be having TCP header or UDP header, let's say TCP header of 20 bytes, then I will be having 1460 bytes of data. So what we do at the transport layer itself, we do not make packets more than 1460 bytes, so that there is no problem till the data link layer, and there is no problem of the fragmentation till the data link layer, right? Which means if we take care of the data link layer protocol at the transport layer itself using some hardware or some software, then we can avoid the fragmentation at the source. But this way, by this way, we cannot avoid the fragmentation in between the routers, because we never know using which path our packet is going to travel. So suppose the packet is going to travel using this path, and this network is not allowing MTU more than 1000, then we cannot avoid the fragmentation in between the router. So there are ways using which we can avoid, which means like there is one field in the fragmentation itself which says do not fragment, and if that field is set, then we say that okay, the fragmentation is not allowed, so packet will get discarded, and there will be some error message that will go to the source that will say that okay, your packet has been discarded because of DF field, because you are saying that do not fragment, so please resend the packet with the MTU size of 1000 only. So there are ways, but in general you cannot avoid just a fragmentation, and you cannot let know about the MTUs of the all the paths in the advance. Even if you know the MTU of all the paths in the advance, then then you are not 100% sure, because IP is unreliable protocol, and it may travel through different paths, using different, I mean the one packet may go to different path, another packet may go to the different path, and there may be different MTUs at different paths. So generally that IPv4 does not prevent the problem of fragmentation. So what we do, I mean the fragmentation either could happen at the source, or it could happen at the intermediate router. So if you have some packet, then based on the data link layer protocol, we are dividing this packet into number of packets, and then suppose this network is having MTU of 1000 or 1500, then I'm dividing this into two packets, but further this network is allowing even smaller packets, which means let's suppose this network is having MTU of 1000 only, then I will do what, or this router will do what, this router will again divide these packets into smaller packets, right? And once all of these packets get reached to the destination, then these packets get reassembled into the original packet. So this is what happens at the destination only. So at the router, we do not do the reassembly, because there is no point in reassembling, and if there is some network that we find that is having MTU lesser than the total length, then again I need to divide that packet. So there is no point of reassembling the packets at the router. And also, like, we do not know if we are getting all the packets to the same router or not, because one fragment may follow one other path, another fragment may follow one other path, right? So we are not 100% sure that every fragment is following the same router. That's why reassembling at router is not useful. So we do the reassembling at the destination only. I hope you got it. So fragmentation can happen at the source or at the router, but reassembly will happen at the destination only. Now see here, this is the size of MTU. MTU means the amount of data that the data link layer protocol is allowing. So amount of data excluding the header. Similarly, MSS means amount of data that TCP or the UDP or any of the transport layer protocol is allowing. So the MSS and MTU is basically amount of data, okay, excluding the headers. Now let's summarize everything what we have studied till now. So in the fragmentation, so the value of MTU determines the amount of data that a data link layer protocol or data link layer frame can carry, is called the MTU, right? So when a datagram is fragmented, each fragment has its own header, as I told you earlier. So each fragment will be having its own header, okay. Now a fragmented datagram may itself be fragmented, which means if you fragment this, then this datagram may itself again be fragmented. It's not like you cannot fragment it further. So you can fragment it as many times as required. A datagram can be fragmented at the source, host, or at any router in between. So a datagram can be fragmented at the source or at any router in the between, right? Now let's talk about the fields related to the fragmentation. So if you remember, there was a second row in the IP header which we have skipped in the last video by saying that we will be studying this row in the like whenever we will be studying the fragmentation. So there are different fields in the fragmentation. Now before I go to these fields, let me ask you some of the question. Suppose there is some packet that you have fragmented into, suppose, different packets, suppose 3 packets, 1, 2 and 3. Now at the destination you are going to reassemble them. This is 1, 2 and 3. Now tell me how you will be sure that these 3 packets which got fragmented are belonging to the same original packet, which means that suppose this is packet number 1, this may be packet number 2, and this packet also get fragmented, let's suppose into 2 or 3, maybe doesn't matter, so let's suppose into 2 fragments. Now these 2 fragments also reaching to the same destination, because let's suppose the source and destination are fixed for both of the packets, which is quite common. Now how you will be sure that on receiving these 5 fragments that you need to combine these 3 and these 2, not this one with this one. I mean, you are not going to combine this one and this one, the first and first. How you will be sure that these 3 are belonging to the same original and these 2 are belonging to the same original? So there you see one need of something called as identification number. So what I will be doing, each packet will be having some identification number or ID number. And let's suppose this ID number is 100 or ID number is 1, and let's suppose this ID number is 200 or 2, something like that. Then I will put the same ID number in each fragment. So this ID number will be 100, this ID number will be 100, this ID number will be 100. Similarly, this ID number will be 200, this ID number will be 200. Now once these 5 packets receives at the router, at the destination, then it will just check the ID number. So based on the ID number, it can guess, okay, these 3 packets are belonging to same ID number, which means these 3 packets are belonging to same original packet, and these 2 packets are belonging to same ID number, which means these 2 packets are belonging to same original packet. So based on that, it can reassemble the packets. So there is one field that is called identification number, which help us to determine which packets are belonging to the same original packet, right? Now suppose that these are the three fragments that this packet got divided into. Now suppose you receive these fragments, then how you will make sure that there is no other fragment? I mean, you need to just assemble these 3 and you should not wait for 4th one. How you will be 100% sure? I hope you got it, right? So what I'm saying, that you have received these 3 fragments at the destination, and how you will be sure that you should not wait for you should not wait for other packet to reassemble. These 3 packets are actually the whole complete packet that you started with. So for that, you see there is some need, and that is done by just one bit, that is called MF, more fragment. So what I say, that if MF is 1, then it means this is not the last packet. MF is 1, then there are more fragments to follow. There are more fragments, right? If MF is 0, then I will say no more fragments. This is last packet basically. And this is last, right? So here I will be having MF1 because this is not last, this is not last. I will be having 0 here. So once I receive this MF1, then once I receive this 0, then I will be 100% sure that, okay, that since I have received the MF with 0 value, it means that this is the last packet and I should not wait for the other packets, right? This is the last packet. So there is one field that so this flags are basically having 3 fields, and the one of the field is MF field, and this field is never used, so this is just reserved. And there are 2 basically bits in the flag, one is MF and one is DF. So MF means more fragments. If MF is 1, then it means there are more fragments. If MF is 0, then it means it's a last fragment. And there is one field that is called DF. DF means do not fragment. DF means do not fragment. So if DF is 1, now let's say if DF is 1, then it says don't fragment. Which means, suppose a router has received a packet which is having a DF H1, DF with H1, and then router has to fragment this packet because of the empty value. Suppose this empty value is 1000, and this packet like data length including the IP header is basically exceeding the 1000, which means let's suppose this is 1500 or something, right, which is exceeding 1000. Now this router anyway has to divide this packet into number of packets, but this DFA bit is saying that like do not fragment, which means router will do what? Router will drop this packet because it is not allowed to fragment, and it will send the error message. So there are some protocols that is called ICMP protocol that we will be studying later. So it will send the error message using the ICMP protocol. It will say that I am not allowed to fragment, so please reduce the size of the packet by you itself. Like, since I am not able to reduce, so you please reduce the packet size to 1000 only, right? If DF is 0, then yeah, this router is allowed to fragment. Okay. So yeah, we were talking about this more fragment, and if that is 0, then you will say that this is the last packet. If that is 1, then you will say this is not the last packet. That is okay. Now, do you think using this identification number and this MF field, you can do the reassembly? Which means using this identification number, you are sure that okay, you need to assemble these 3 packets, and you should not wait for any more packet. Which means if MF is 0, then you should not wait for any more packet. That is okay, but still, it does not solve the complete problem. There is one issue. The issue is that suppose you are sending 3 packets, okay, I mean this packet got fragmented into 3 packets, and you are sending this 3 packets. Here MF bit is 0. I'm just writing MF bit, not identification and do not fragment. So I'm only writing the MF bit. Suppose these are the MF bits, and this MF bit is 1, this MF bit is 1, and this MF bit is 0, because this is the last fragment. But suppose something has happened and only this fragment, first fragment, got reached where MF is 1, and the last fragment got reached where MF is 0. Then am I allowed to club this without this intermediate fragment? No, right? I cannot club this because intermediate fragment and any fragment which is missing, without which I cannot club the fragments to make the original packet. So how would the destination get to know that there are some missing packets? Because destination, according to the destination, the ID number is matching, which means it will club this. Since this is not the last packet, it has received the last packet, but how it will be sure that it has also received the intermediate packets, right? So it has received the last packet will be given by this MF bit is 0, but how the destination will be sure that it has received last packet also? Sorry, it has received all packets, I mean intermediate packets also. So that is done by offset. That is done by offset. So offset fields tells us that this packet should be followed by how many bytes. So suppose that there is some packet that got fragmented into 3 packets, 1, 2, 3. Here, let's suppose this is the first packet which is having MF bit as 1. This is the MF bit. This is again MF bit. Then this is the MF bit as 0. And now they are traveling to some path, and suppose there is some network in the between that again has to fragment this middle packet. Like this middle packet is getting routed by this way, and like the packets may get routed by other ways based on the dynamic structure of the network. So suppose this packet and this packet are getting routed by this way, which means this packet and this packet are getting routed by this way, and obviously the destination is same for both of, like for all of them, and this middle packet is getting routed by this way, suppose. And in this way the MTU is even smaller, so this is again getting fragmented into 2 fragments. So I started with original packet. This original packet got fragmented into 3 packets. Now I'm saying this is also getting fragmented 2 packets, right? So total how many packets I have? Total I have 5 packets, sorry 4 packets, 1, 2, 3, 4 packets. Now can you tell me the MF bits? So identification will be same for all of them, and let me write the MF bit. Suppose this is the first packet, so let me write the, sorry, this is the last packet, so let me write the MF bit as 0. This is the middle packet, MF bit as 1. This is middle packet, MF bit as 1. So what do you think? This, let's suppose this is the first like first to last packet of the middle packet. So it does not matter, basically it will just copy the MF bit, because if this MF bit is 1, then it will say that okay, like there are more fragments to follow, so that's the way it will just copy this MF bit. It will not write 0 here, this because this is not the last fragment, right? So these are the MF bits. Now I have 4 packets. This is packet number 1, maybe packet number 2, this is packet number 3, let's suppose packet number 4. I have just randomly, I'm just saying the packet numbers, that does not make any sense for the destination. This is just for our purpose. I have written 1 2 3 4. Okay, now my question is that how will you or like destination get to know that how many number of packets are there? So that is given by the offset. Suppose that this is the packet, and you say that okay, let me write 1 2 3 4 in this way, because I have given this as a packet number 1. So let's suppose this is the first packet, this was the second packet, and this was the third packet earlier, right? But now this is the first packet, this is the second packet, this is the third packet, and now this is the fourth packet. Now what I'm saying, let's suppose that you are saying that this is the first packet, second packet, third packet, and like that, and you are giving it this as a fourth packet, right? So you will be doing what? Once you receive these packets, you will say that okay, this is the fourth packet. I mean, you will be waiting for MF bit at 0. So MF bit 0 is having the packet number as 4, suppose. Then you will say that okay, there are total 4 packets, right? But you never know if this packet again get fragmented into number of bits, number of packets. Then there will be 5 packets, right? But you cannot change this packet number 4 based on this scenario, right? You're getting my point? So if this is 4, let's suppose this is 4, then if this again gets fragmented, then the total number of packets are 5, not just 4. So how you will say, how you will change this 4 based on this fragmentation? You can't just change this 4, because you do not keep track of every packet in the every path or something, right? So this strategy will not work, which means numbering the packets will not work at all. Because if you number the packets, and if the intermediate packet get fragmented, then how you will be changing these numbers? So numbering the packet will not work. Then what else will work? So there is something called offset. So offset will tell us that how many bits or how many bytes this packet is following, which means, let me go to the next page. So there is a field called offset that tells us that how many bytes of data, or let me write IP data, how many bytes of IP data, which means apart from IP header. So IP data, the particular fragment is following, particular packet is following, which means suppose there is some packet that is having data of 5000 bytes, suppose, right? And this is the IP header. Now let's not worry about the IP header length. It may be 20 or 30 bytes, any number of bytes. Let's not worry about it. So this is the IP data only, and this is IP header. And because let's suppose the MTU is let's suppose this is 20 bytes and MTU is 1500 bytes, which means this is the data size that the data link layer can carry, which means you need to divide this IP data into 480 each, right? 480 each, because 480 plus 20 will be 1500, and you cannot carry more than 1500. So you will be dividing this into 480. So there will be like this will be some number, and there will be 4 packets. Now what will happen? Let's suppose this is the packet number 1. This will be having some MF value, some identification, some of the fields. So this is the packet number 1, and let me write it in the smaller font. So suppose this is the packet number 1, this is the packet number 2, this is the packet number 3, and let's suppose this is the packet number 4. Now tell me how many bytes are there, since this is a packet number 1. So how many bytes are there after the packet number 1? So how many bytes it is following? So no number of bytes it is following, which means the 0 data byte it is following, right? And how many bytes it is following? How many bytes it is following? Data bytes only data bytes, IP data, excluding the header. So it is following 480, because this is 20 bytes of IP header and 480 of data that we have. So it is following 480 data bytes. So that's why offset is 480. So offset is 480 here. Why? Because it is following 480 bytes. And how many bytes it is following? After it is 480 for this, because like don't consider the IP header, okay? Only consider the IP data. It is following 480 bytes here and 480 bytes here. So 480 into 2 it is following. How many it is following? It is following 480 into 3, right? So this is the offset. I hope you got it. So how many bytes this packet is following is the offset. How many bytes this packet is following is the offset. And what about the more fragment field? So more fragment, yes, there are more fragments. Yes, there are more fragment, and there is no more fragment. So it will be having 0. What about the identification number? Suppose the original identification number was 100, so everyone will be having 100, 100, 100, 100, right? So these are the fields related to this row. I mean this row field: identification number, more fragment, and fragment of offset. I hope you got it. Now, how it will help the destination? At the destination, when you receive the like how it will help the destination in the sense that how the destination will get to know that there are intermediate packets or not. So destination will get to know that this is the last packet, and destination should also get to know that the destination has received all intermediate packets. So destination will search for the offset 0, and then it will say that okay, that it will calculate the number of bytes here. The number of bytes here are 480. Then it will search for the packet which is having 480 data bytes as an offset. So it will say that okay, it has received. Now it will search for the next packet which should be having the 480 into 2 data bytes, and then it will search for the next packet which should be having the 480 into 3 data bytes as an offset. I hope you got it right. So like if I write the reassembly code, then destination will look for uh, search for offset 0, right? I mean search for offset, and let me write the some pseudocode. Initially the offset is 0, right? Search for the packet which is having offset. Now this offset, once it finds, then it updates the offset with, now it is going to search for the offset plus the number of data bytes in that packet, right? And the searching will get stopped whenever it like repeat till mf is 0, which means till it finds the last packet. That's how it is going to do it, and this will search only within the packets which is having the same identification number, with the same identification number. That's how the reassembly will work, right? It will keep on searching the packets with the same identification number. It will basically make a pool of identification number. So it is, these are the packets with the identification number 100, these are the packets with the identification number 200, and within the 100 only it will search for the offset 0, then offset 480, then offset 480 into 2, like that till it finds the packet which is having the mfs 0. That's how the reassembly will work. So now there is no ambiguity at the receiver side or the destination side, that how to assemble all the packets. And that's how all these fields are helping us. I hope you got it. Now let's solve some of the questions. So just to revise, basically identification is to match with the other fragment, and these are the two flags that we use. Like flags are basically 3 bits. One we never use, and this one is more fragment, this one is do not fragment. Or maybe like first one is do not fragment. Let me quickly check it. The first one is do not fragment, or the second one is do not fragment. Okay, I will just check it in a while. So either the first one is do not fragment or the second one is do not fragment. And if one of them is do not fragment and one of them is more fragment. And fragment offset is basically telling us that where this IP datagram, this fragment lies within the IP datagram. Now there is one catch. If you just notice that fragment offset is just 13 bits. See here, this is just 13 bits because these are the 3 bits, so remaining are 13 bits, which means I can just say like 2 power 13 bytes as a maximum fragment offset, which means this datagram can maximum follow 2 power 13 data bytes after it, right? Because the fragment offset can have maximum value as 2 power 13. right? But my total length is basically 16 bits, which means it can have 2 power 16 as a total data. So you see the problem. See here what is happening. My total length could be 2 power 16. Now this is, since we are designing the IP header, so you should not worry about the data link layer header. So the limitations are provided by the data link layer header, but when we are designing the IP header, then we should not worry about the data link layer header. Maybe in the future some data link layer protocol is allowing total length to be 2 power 16. Then we should be ready for that, right? Now suppose that this is the packet that we are having, and this packet is basically actually having the total length of 2 power 16, right? Now this packet gets fragmented, and then this is the last packet that we have in the fragment, which is actually just having 1 byte. I mean, minimum number of bytes it can have. So these are the number of packets that I have after this last packet. So tell me how many bytes this last packet is following. Since the total length is 2 power 16, so this last packet is almost following 2 power 16 minus 1 or something like that. I mean, in the range of 2 power 16 only, because the total length is 2 power 16. Then it should be following, like if let's suppose this is 20 bytes, so let me be very specific. Then the data size is 2 power 16 minus 20, and since 1 byte I have given to this, so it should be following actually 2 power 16 minus 21. Anyway, this 21 is very small number compared to 2 power 16, so it is actually following almost equal to 2 power 16 bytes. So the fragment offset here should be 2 power 16 minus 21 or whatever, right? It should be like approximately 2 power 16. But my fragment offset field is allowing only till 2 power 13. So the minimum it is allowing 0 and maximum it is allowing 2 power 13, and minimum I can have 0 and maximum I can have 2 power 16, right? This is the actual thing I can have as offset, and allowed offset are this is the allowed offset, right? And this is the actual offset I can have. So let me write it here. These are the allowed, which means I can have only 0 to 2 power 13, and this is the actual. Actually in practical I may be having 0 to 2 power 16 only. So what is the solution? Like, how can I represent this 2 power 16 as a number in this 13 bits? I cannot represent, right? So what is the solution? Is, let me just give you a hint. Like this is not the new problem that we are facing. We have already faced this kind of problem in the header length. So if you remember, the header length, not the total length, the header length actual or allowed was only 4 bits, which means 0 to 15 I was having allowed, and actually it can have from 20 to 60 bytes. So what we did, if you remember, we scaled it down. So whatever was our actual, we divided by 4, and then we got some number, and then we are writing in the header length field, right? So if my actual header length is 5 bytes, then I will just say, sorry, if my actual header length is, let's suppose, 20 bytes, then I will just say that dividing by 4 will give me 5, so I will just represent 5. Similarly, I will do the same thing here. So if my actual is 2 power 16, then I will divide by actually 2 power 3, 8. So basically I will divide by 2 power 3, and whatever number I get, which is in this case 2 power 13, then I will represent that number in the 13 bits, and that I can do it, right? So whatever is the actual total length, whatever is the actual fragment offset, I will divide it by 8, and then I will write as a fragment offset. So if I say that my fragment offset earlier, if I say that my fragment offset is 480, then this is wrong. Basically I will say that my fragment offset field will be containing, I mean, the fragment offset may be 480, but it will be containing 480 by 8 as my field. So by 8 I need to divide. I hope you got it, right? So if you divide by 8, then you will be getting how much? 480 by 8. Let me quickly do it. So just divide by 4 first. This is 3, then this is 7, 0 by 2, then you can divide by 8, which means it is basically divisible by 8. So yeah, that is, there won't be any problem because these numbers are divisible by 8. Okay. Now there might be some cases when the numbers are not exactly divisible by 8. Suppose that number is not exactly divisible by 8, so you cannot have this as a fragment offset. You need to just adjust it to the lower value so that you can divide by 8. So we will be seeing it in the examples. Now let's do some of the examples. So let's say that a packet has arrived with m bit as 0, which means there are more fragments. Mf bit or m bit is 0. Are there more fragments? No, right? So it means this is the last. Is this the first fragment or the last fragment or the middle fragment? Do you know the packet is fragmented? Okay, that's a nice question. So what do you think? If this is 0, then is this a first, last, I mean, which kind of fragment it is? Since that m is 0, then there are no more fragments, that I'm sure. Which means this is definitely either last fragment, or you can say that this is either original fragment, which means that there may not be any fragmentation at all. So you will say that this is either last or no fragmentation at all, which means the originally my packet should be containing 0 only. I mean, from the source itself it should be containing 0 in the more fragment field, right? So you can say that either this is the last packet or the packet was not fragmented at all. Now let's go to the next question. A packet has arrived with a more fragment field as 1, which means this may be the first fragment or maybe the middle fragment. So here you can say that it means that at least one more fragment is there. So it is either the first fragment or the middle fragment. Do you know the fragmentation has happened? Yes, we know. So we will say that yes, fragmentation has happened, and this is either the first fragment or middle fragment. Okay. Let's solve this question. A packet has arrived with more fragment field as 1 and the fragment offset value is 0. Okay. So they are saying the fragment offset value is 0, which means this packet is following 0 bytes, which means this has to be the first fragment, right? And then they are saying the more fragment field is 1, which means there are more fragments after it. So it is definitely the first fragment and the fragmentation has happened, right? So we will say that because the m bit is 1, the first fragment, this is either the first fragment or middle fragment, but since the fragment value is fragment offset is 0, then you will say that this is the first fragment only. So you will say this is definitely the first fragment, right? Now let's solve more question. A packet has arrived in which the offset is 100, which means after that there are 100 bytes, maybe in one packet, maybe in different packets. I mean, there are 100 bytes, maybe the one packet is containing 100 bytes itself, maybe the different packets are containing 100 bytes, but yeah, after it there are 100 bytes. Okay, so it is saying the offset value is 100, which means, yeah, which means what? There are actually not 100 bytes, there are 800 bytes, because I must have divided by 8, then I must have put this value. So what is the number of first byte? What is the number of first byte? Do we know the number of the last byte? So, okay, so they are saying that what is the number of first byte, which means that if we just number every byte, then like there are 800 bytes after it. If we number every byte, which means 0 to 799 bytes are after it, and the number of first byte here will be 800 if we number every byte. And what is the number of last byte? We do not know, until and unless we know the length of the header and length of the like total length of this packet, then we do not know the size of the data. So we do not know the last byte, we do not know the last byte, but yeah, we know the number of first byte, which is 800, right? So let's solve this question. A packet has arrived in which the offset value is 100 and the value of header length is 5 and the value of the total length field is 100. Yeah, this is a good question. So offset is 100, which means there are 800 bytes that are following after it. So there are 800 bytes, which means 0 to 799 bytes. And what are the number of first byte? So header length is given to us, which is 5, which means the header length, actual header length is 20 and offset value is 100, which means the actual offset is basically 800 and total length field is 100. So what you can say about the data, if this is 20 as a header and total length is 100, which means you have 80 bytes of data, right? 80 bytes here. What are the numbers of first and last byte? So you can definitely say that 0 to 799 bytes are after it, and this should be 800 bytes. 800 byte, let me write it 0 in the leftmost corner. So this is 0 to 799 and this is 800 byte. And can you comment about this this byte number? Since these are the 80 bytes, so you can say that this is 879, right? These like this is the byte number for this last byte. I hope you got it. So last byte number is 879. Now, now these are the solutions that we have for all of these questions that we just did. Now let's solve some practical questions where I have the MTU and I have some of the like header size and the data size and these all, and then how to do fragmentation. So we will be doing this in the next video.